Good morning, everybody, and welcome back to Abstract Algebra. Plan for today, we're going to do it. We're going to start our second of the two major units in the semester, and today we are going to talk about rings. I've got my usual office hours on Monday, 10 o'clock in at 2. Don't forget, homework 6 is due tonight. So make sure you have that in and submit it to Blackboard by 11:59 p.m. Any question? I kind of already asked that, but now that we're officially being filmed, does anybody have any questions or comments before we get started? All right. Student goes up to his math teacher one day and says, Smith, I agreed to solve equations. I agreed to prove theorems. I even agreed to do some statistics. But graphing? That's where I draw the line. Okay, so like I said, today's going to be our big turning point in the semester where we go from talking about groups to talking about rings, which, not completely different subject. Rings are just groups with a little bit extra. Main difference between a group and a ring is that in a group, we just have a set with a single binary operation, a single way of taking two elements and combining them into a new element. In a ring, we're going to have two. We're going to have two different binary operations, one of which we'll call addition, and one of which we'll call multiplication for short. So let's write this out. A ring, which we're going to denote by using R, and the two operations, I'm going to refer to one with a plus sign, one with a times sign, and we're going to call them addition and multiplication. But as you'll see, addition and multiplication might not be the way you're used to thinking about them just in terms of real numbers. But a ring is going to be a set. It is a set R equipped with two binary operations. Plus and times, such that, first of all, we want R to form an abelian group under addition. So that automatically means that R has to have closure under addition. If you add any two elements in R, you'll get back something in R. It's going to have associativity. Addition's associative. It's going to have an additive identity element, and it's going to have additive inverses. Second condition is that R is closed under multiplication. And third, I'm going to say multiplication is associative on R. So in other words, we want our ring to be a group under addition, an abelian group. So things commute under addition. We want to have a couple of the properties of a group under our other operation, multiplication. Specifically, we want to have closure. We want to be able to multiply any two things in our ring, get back something in our ring. We want to have associativity of multiplication. A times BC, A times B times C is equal to A times B times C, because those are very nice things to have. However, we're not going to necessarily require that we have a multiplicative identity or multiplicative inverses. So while it's going to form a group under addition, it's not necessarily going to under multiplication. And the last condition that we want is going to be one that kind of combines the addition and multiplication operations in a way, and that's going to be the distributive properties. Properties because there's technically two of them. And what these properties say, first one says that if you were to add two elements, A and B, and then multiply by C, you're always going to get the same thing as A times C plus B times C. And then the second one is basically the same, but in reverse. If you take A and you multiply by the expression B plus C, we're going to get A times B plus A times C for all A, B, C elements in R. So in other words, a ring is basically just going to be a set where you can play around with multiple operations, where you have an addition operation and a multiplication operation, and they satisfy a bunch of properties that you would want addition and multiplication to have. Namely, under addition, you get everything that goes with having an abelian group. Under multiplication, you get closure and associativity. And addition and multiplication behave nicely with each other in that you have these distributive properties. That tells you what happens if you're trying to do addition and multiplication at the same time. So let's look at a couple examples. Anybody think of a classic example of something we've seen to be a group, but also has a multiplication operation that kind of behaves in some nice ways? So what would be an example of a group that we've seen so far this semester that we could also define multiplication on very easily? Okay.
Integers.
Integers, the classic example. Yeah, and this is kind of the classic prototype example of what a ring is. We can define our ring to just be the set of integers under integer addition and integer multiplication. So here addition and multiplication are going to be our usual ones. We have usual addition and multiplication, meaning the way you add and multiply integers is the way you're used to thinking about adding and multiplying integers. And in fact, the whole definition of a ring was built with the integers in mind. Meaning we said that originally groups were designed with integers in mind, and that we wanted to have sets of geometric objects that behaved like the integers under addition. A ring was defined in the same way with the integers in mind, in that we want rings to basically be sets of objects with these operations, addition and multiplication, that behave just like the integers do. So that's kind of our classical example of a ring. What would another example be? Something else, another set of things that you can add and multiply in a way that'll make all of this turn out nicely.
Did you just use the real numbers?
Sure. You could also just take the ring of real numbers. And that's under the usual real number addition and multiplication. Kind of another classic example. So here's an example that maybe you're a little less comfortable with, but one that that's shown up a couple times over the semester. Fancy looking P. Anybody remember what that is? What the fancy looking P stood for as a group? Yeah, the group of all real polynomials, or as we're going to be referring to it now, the ring of all real polynomials. So in other words, P, we're saying, is going to be the set of all functions of the form f of x equals an x to the n plus a sub n minus 1 x to the n minus 1 plus a1x plus a naught, where all of the a sub I are going to be real numbers. And I claim this is going to form a ring under addition and multiplication of polynomials, where the operations work kind of the way you're probably used to. If we were to take, say, x squared plus 1 and add to that 3x squared minus 5, What would we get if we added those two polynomials together? Okay.
4x squared minus 4?
4x squared minus 4. Yep. So you would just add these the way you normally would, just combine all the like terms. And you can also multiply. So this is something you saw way back on the first homework of the semester as an example of a group under addition. Turns out, also going to form a group under multiplication, or not a group. It's also going to satisfy the ring properties necessary for multiplication as well. Because we could take something like x squared plus 1 multiplied by, I don't know, 2x plus 5. And you would multiply the way you normally would, just kind of FOIL it out. So you would end up with 2x cubed plus 5x squared plus 2x plus 5, I believe. But polynomial addition and multiplication kind of work out in this nice way that's going to give us a ring. So we have a group under addition, we have closure and associativity for multiplication, and we have these nice distributive properties that tell us adding and multiplying kind of in the same equation will work out the way you might want them to. Just like how real number addition and multiplication kind of works out. So question, these are all things we said were groups under addition. Are any of those going to form groups under multiplication? That's why I need Elaine and Lauren here. How about the risk? By a show, as I point to the integers, by a show of thumbs up or thumbs down, is this going to be are the integers going to form a group under multiplication? It's kind of one of our big counterexamples we've seen before. It does not. Why does Steph, why don't the integers form a group under multiplication?
Well, it has to be non-zero.
Okay, do the non-zero integers form a group under multiplication?
Yeah.
So what's going to be the multiplicative inverse of 3?
What?
So if everything has inverses, what would be the inverse of 3 under multiplication?
I'm confused.
I think even if you take away 0, it's not going to form a group because you won't have inverses. Because multiplicative identity would be 1, but then things like 3 wouldn't have an inverse because the only thing you could multiply 3 by to get 1 would be something that's not an integer. So this is not going to be a group under multiplication. For one, because 0 has no multiplicative inverse. How about the reals? Show thumbs up for yes, thumbs down for no. Are the reals going to form a group under multiplication? Also seeing some thumbs down. Sally, it looks like you changed your vote a little bit.
I'm not sure.
Not sure. So why don't the reals form a group under multiplication? Something I'll go.
I mean, they do if you eliminate 0.
And problem is 0. 0 has no multiplicative inverse, just like with the integers. How about real polynomials? Do they form a group, yes or no, under multiplication? Dave's coming out strong. Why not?
I don't remember exactly, but I think they have problems with their identity. No, the inverse is also.
I'll say identity's fine. You could just take the constant polynomial 1 to be the identity. But I think, yeah, we're going to have trouble with inverses. For instance, 0 has no multiplicative inverse. That's a common theme. I wonder if that's true of all rings. So, in general, when you have a ring, it has to be a group under addition, but it does not have to be a group under multiplication. Multiplication does need the first two group properties, but you don't have to have a multiplicative identity, and you don't have to have multiplicative inverses. Professor Pytel makes weird noises. Any questions about what the definition of a ring is? Yes?
Is it a special case if it's both works for both addition and multiplication? Or is that just, or is that?
It is a special case, but I'm not going to reveal what that special case is just yet, because that's going to be something we're going to prove here just a little bit. Yes, there is something special that happens when you have a group under multiplication and a group under addition. All right, got a challenge for you all. I want you to take a couple minutes and look at the next couple pages. I'm going to give you several examples of sets that have an addition and a multiplication operation defined. I already did the first one because we spoiled it. But like R3, where addition is the dot product, multiplication is the cross product. M2R, the ring of all real 2x2 real matrices with matrix addition and multiplication, etc. I want you to look at the next two pages and see if you can determine which of these are rings and which of these are not. I'll go ahead and write them down on the board in case you don't have your pen. Take just a couple minutes and see which of these you think are rings and which of these you think are not.
Doesn't the dot product not give you something in R3? It just gives you a number, right? You get a dot product. Yeah. So then it doesn't form a dealing group under C.
Did it?
Because it's not.
Yeah.
Yeah.
It does. You could multiply to get a polynomial greater than 3.
Okay. Is matrix multiplication associated with a number?
It is indeed.
We did the first one.
Well, then my gut feeling would be that would work because you're just adding and multiplying 4 things at once.
Oh,
Because you can add them both ways. So if you multiply it, you're not going to get like a 4 by 4.
Yeah, because those are the part of the root box.
What? It is. What's G? Well, actually, wait.
is this condition supposed to be multiplication or not addition? I mean, when we do that,
Is what comes under?
we do addition or multiplication.
Oh, addition is the one that has forms.
You have to have you end up having to have closure under both operations, keep in mind.
Right.
Addition is so that it becomes a group, multiplication because that's property number 2.
So I don't think that this one wants to be part of the dot product.
What is GL2?
Not zero.
Oh, it's not 0.
It's just a special case.
I feel like this
Okay.
one does. Only because any real matrix, so it could be like 0, 0, 0.
That's why I said yes or no.
You multiply them, can you make sure that the determinant one stays 0? Or won't become 0?
I feel like this one's very specific.
Yeah, because the multiplication. Does it? Would it still be true for addition? If you
No.
add 2 matrices.
Yeah, because you can add them, you can just add them, yeah, and then you get 0. So that doesn't work.
So this one isn't gonna work because of association.
Okay, I don't think the polynomial is listening to work because if you multiply them, you get an entire degree polynomial. How does mod affect?
For those of you watching this at home, Try this out for yourself. And remember, you got this.
Modding stuff is not.
You think the mod would be fine?
Not associative, so I feel like that's.
I feel like this one's very specific.
This one.
Which one is very specific?
This one.
Well, that one's one we haven't really talked about, so I felt like I need to go out and define in great detail.
This is very specific.
I mean, all of these are very specific. You know how long it took, remember how long it took us to define Z mod NZ?
That's true.
That took us way, that had way more involved. It's just that I didn't include any of the,
Because you lied at first.
I lied first, yeah, no. I'm kind of lying again right now, actually, because technically it's addition and multiplication of cosets mod.
I just thought his.
And here's again.
No, I guess it
But I don't want to talk about Zmod NZ, the ring, well, spoiler alert, it's a ring, but everybody's getting quiet looking at me. We haven't talked about quotient rings yet, so. Oh yeah, that's a thing.
That's a
No, quotient groups are bad. Oh, just you wait. That's the next packet, actually.
What was it that I saw reading this before? I think it was in mathematical.
Maybe it was on your finger.
Could be. I wish.
All right, let's come back together and talk about some of these. Sounds like we've had a chance to look at a lot of these now. How about this one? R3, where addition is the dot product and multiplication is the cross product. Any thoughts on that one? Thumbs down?
Thumbs down.
Why is that?
Because the scalar is also scalar.
The scalar is also scalar.
Yes. That was,
I'm not sure what that means.
she helped me with that. Called tagging, phoning a friend.
Oh, throwing Megan under the bus, huh? Okay, Megan. Why is a scalar is a scalar?
When you multiply things in R3, a dot product gives you a single number, and the cross product gives you a matrix or vector.
Yeah, cross product of two vectors in R3 will just be another vector in R3 in all cases. But you don't like the dot product?
Yes. No, I do not like it.
No, you do not like the dot product.
Yes.
Yeah. So it turns out this set is not closed under addition, so it's not. Where addition is, and by addition I mean the dot product. E.g., if we were to take the dot product of 1, 2, 3, and 4, 5, 6, we would get something, we would get what? 4 plus 10 plus 18 equals 32, which is not an element in R3. So R3 does not form a ring under where addition is the dot product and multiplication is the cross product. Mainly because it doesn't form a group under the dot product. Which I think you all had on your first homework. How about the set of all 2 by 2 real matrices under addition and multiplication of matrices? Anyone other than Megan want to stake a claim? Okay,
Yes.
it is?
Yeah.
So, we already know that this forms a group under addition. We've talked about that one before. So you're saying matrix multiplication has closure, meaning if you multiply any two 2 by 2 matrices, you're going to get another one.
Yes.
You claim matrix multiplication is associative.
Yes.
I told you that one. And you claim that it satisfies the distributive problem.
Maybe, but I didn't think about that one.
Uh-oh. It does work.
Okay.
Yep. So the ring of all 2 by 2 real matrices is in fact a ring. Because it does everything we want. Doesn't form a group under multiplication, but it is a ring. How about GL2R? Our good old faithful friend GL2R, the set of all invertible 2x2 real matrices. Is that going to form a ring?
No, because it's not closed under addition.
Bingo. No, for the same reason as the last one. Not closed under addition. Can you give me an example of a couple 2x2 matrices in GL2R whose sum is not?
Yes, the identity and negative identity.
Okay, that's a good one. It's exactly the one I had in mind, in fact. So for instance, identity matrix and the negative of the identity matrix are both in GL2R, but the sum 1, 0, 0, 1 plus negative 1, 0, 0, negative 1, which would give us the 0 matrix, is not GL2R. So it fails closure. It also fails to have an identity element because this is what the identity element would have to be under addition, and that's not in GL2R. So couple ways in which that one fails.
I know Nick's not here, but if you give me a few minutes, I can probably find more complicated examples.
Gosh, that's true. I need a lane to crack the jokes, Lauren to laugh at them, Nick to try and trip me up with counter examples. That's kind of all the boring students left. Wow, that was really mean. I should just still. All right. Set of all polynomials of degree less than or equal to 3 under polynomial addition and multiplication. We said the set of all real polynomials works. What about polynomials where we're restricting the degree to be less than or equal to 3? Okay.
It's not enclosed under multiplication.
It's not closed under multiplication. Gadzooks. Prove it.
Well, if you've got x cubed and you multiply it by x cubed, you get x to the 6th, which is not less than or equal to 3 in degree.
Ooh, sounds good. I like it. Yeah, so this one does form a group under addition, but it fails to be closed under multiplication. So no, so not closed under multiplication. And example, sure, that one works. We could say that x cubed is in this set, but x cubed times x cubed, which would be x to the 6th, is not a polynomial of degree less than or equal to 3. Which is fine. Any questions or comments on any of these first few examples? Let's get to the more fun ones then. How about Z mod NZ? Our good old friend returning once more. Under addition mod n and multiplication mod n. Thumbs up for yes, thumbs down for no. We're voting in 3, 2, 1, go. Ooh, some more controversy here. Let's see. Megan, you had a thumbs down. Why do you say no?
I'm not 100% sure about this, but I think that in like mod n, you don't have associativity.
You don't think we have associativity with multiplication mod n? Uh-oh. You do, as it turns out. Basically comes down to the fact that if you remember the group of units mod n, that we said that was a group under multiplication mod n, that kind of relies on being able to have associativity mod n. It's a complete pain to actually go through and prove, but associativity, multiplication mod n does indeed have associativity. Are there opinions on the matter? This one checks out, actually. Z mod NZ does form a ring under addition and multiplication mod n. We do have closure mod of multiplication mod n. We have We have associativity of multiplication mod n. The distributive properties do in fact work out. And we know Z mod NC is a group under addition mod n for reasons we've already talked about. Finally, how about this lovely example of a set of all continuous real functions under addition and multiplication, basically the same as how addition and multiplication work in this example. You add or multiply functions by just kind of taking their outputs and adding or multiplying together. By a show of thumbs, yay or nay, voting in 3, 2, 1, go. Okay, another pretty split opinion.
Oh, it just felt too good to be true.
It felt too good to be true. You couldn't find one of the four though that you thought necessarily failed?
No.
This one does feel too good to be true. This is a very big ring, if it is in fact a ring. Ring of all real polynomials, or not even polynomials, continuous functions. There's a lot of those, like e to the x and the trig functions and inverse trig functions and yada yada yada. But it does check out. Let's go. So here, this is a ring where you could do interesting things. Like we can take if f of x equals, I don't know, sine of x, and let's say g of x equals e to the x plus x. We could do things like we could add these, and we would get something like sine of x plus e to the x plus x. What would multiplication be? If I were to multiply this f of x and g of x together, what would that give me? And by me, I mean you, because I'm asking you all to tell me what this is. Your hand is going up ever so slowly. I've never seen such a slow hand.
Is it just sine of x times e to the x plus x?
Yeah, just multiply this expression by this expression. So that'll give us sine of x times e to the x plus x, which, using the distributive properties, is going to give us sine of x times e to the x plus sine of x times x. Boom. There's kind of another classic example of a ring of all continuous functions over the reals. So we've got lots of examples here of sometimes we have some groups from the group portion of the class that translate nicely into being able to talk about rings. Things like Z mod NZ kind of has a natural ring structure to it as well as a group structure, and that multiplication mod n works nicely alongside the addition. Ditto with like the ring of all real polynomials, M2 of R kind of set of all 2 by 2 real matrices kind of extends naturally from having an addition, just an addition operation with a group to having addition and multiplication with a ring. There's lots of examples of groups we've seen that don't really have nice ring structures to them, like the dihedral groups, the symmetric groups. Kind of don't really have natural multiplication operations in addition to the group operation they started with. But a lot of the groups you study do become rings pretty naturally, I would say. All right. Do any of the things we said were rings form groups under multiplication? No, I don't think so, Dr. Burstel, but that last example's too scary for me to make an opinion on. I mean, is that your thought process pretty much?
Exactly.
No. None of these form groups under multiplication, other than GL2R, but GL2R is not a ring anyway, so it doesn't count. So next up, I want to prove some properties involving rings. So if you flip the page, I'll go ahead and write this out. This is going to give us this next theorem is basically like 8 theorems in one because I'm too lazy to write out theorem in bold before each one of these. Next, this kind of result tells us something about how rings have to behave if you have something with a ring structure. So here's the theorem. We're going to let R be a ring. And we're going to let A, B, and C be elements in the ring. And now we're going to say if 0 is the additive identity in the ring, because any ring forms a group under addition, so it has to have an additive identity. In other words, an identity element in the group under addition. Then, first of all, I claim A times 0 has to be equal to 0, which is equal to 0 times A. In other words, if you take the additive identity in your group and multiply it by anything else in your group, you're going to get back the additive identity. That's a bit of a mouthful. Because that's not only telling, that's like, you might look at that and say, Dr. Gerstle, duh, 0 times anything is always 0. But that doesn't just apply to the number 0. That would apply to the 0 matrix in the ring of 2 by 2 row polynomials. Correspond to 0 in Z mod NZ. Whatever the additive identity element is in your ring, if you were to multiply by anything else in the ring, you're always going to get 0. Back the additive identity, in other words. And this one we're going to prove once I state the whole theorem. So next one is going to be if we multiplied A times negative B, we're going to get the same thing as negative A times B, which is the same as the negative of AB, where negative X is the additive inverse of X. So basically saying negative X is the element in R such that X plus negative X is going to give us 0, the additive identity. So basically saying if we were to take the additive inverse of B and multiply by A, we're going to get the same thing as if we were to take the additive inverse of A multiplied by B, which is the same as the additive inverse of A times B. So in other words, we can make a relationship between the additive identity and the additive and addition in the ring, as well as multiplication, no matter what your ring is. Why do I need to specify, by the way, before we just said the identity or the inverse of an element. Why am I specifying here the additive identity of our ring or the additive inverse? Why do I need to specify that, do you think? Got it?
Is it just because you don't need to have an inverse or identity in the multiplication?
You don't, but you could. So you could have it's because the reason why we have to specify additive identity and additive inverses here is because since we have multiple operations, you could have a multiplicative identity and multiplicative inverses potentially as well. And you need to specify which type of identity, which type of inverses are you looking at whenever you're talking about your ring. So the next one basically says negatives cancel out, that if we were to take the additive inverse of A and multiply by the additive inverse of B, that's just the same as taking A times B. By the way, if I ever write out like AB like this, that's A times B, where times is the multiplication operation in the group. And finally, here's a fourth property. A times B minus C is going to be equal to AB minus AC, and B minus C times A is BA minus CA. What is this? Dr. Gerstle, you just introduced a third operation, subtraction. So what do you think I mean by subtraction here? If I were to say A and B are elements in the group, and I wanted to take A minus B, what does that mean? Here?
A plus the inverse of B.
Plus what inverse? Additive or multiplicative inverse?
Oh, additive.
I'd say, yeah. We're not used to having to think that way. We're used to just being able to say inverses because that's enough to know what you're talking about in groups. But rings, you always have to specify. Yeah, so by definition, this is just going to be A plus the additive inverse of B. So we kind of, subtraction just kind of works kind of the same way addition does, but you're just doing it with the inverse of an element instead of the other way around. So that's some properties that any ring is going to have. There's also a few more I'm going to talk about. So let's see, that's the next one. In addition, if R has a multiplicative identity, which typically, if you have a multiplicative identity in a ring, you just call it 1. Why? Because 1 is the multiplicative identity in the integers. 1 times any integer x will always give you back x. Similarly to why we call the additive identity 0, it's because 0 is the additive identity in the integers. So in groups, we're used to just calling the identity element by the letter E. In rings, typically you use 0 and 1 instead to refer to the additive and multiplicative identity, respectively. So if R has a multiplicative identity 1, because remember, rings don't have to have multiplicative identities, that's not part of the definition, which we call unity. I don't know why I put that down, because I'm never going to call it that. Book sometimes does. Then, -1 times A will always be equal to negative A. What's -1? Having too much fun over there. We need to laugh more. Dave, get on that. What do you think I mean by -1 specifically? Because I established what 1 is. 1 is just the multiplicative identity. But what should -1 be in an arbitrary ring?
Is it the additive inverse of the multiplicative identity?
It is. Well put. I was hoping I'd be able to trip you up by saying which inverse which identity, but you said it very well. The additive inverse of the multiplicative identity. I'll write that on the document. -1 equals the additive inverse of 1, which is the multiplicative identity. So, as a quick example, if we wanted to look in the ring of all 2 by 2 real matrices, what would the multiplicative identity be in that ring? Which matrix can you multiply by any other matrix and always get back that other matrix? The identity matrix. The multiplicative identity specific matrix specifically. So 1 here is just going to be the 1, 0, 0, 1, because that's the matrix you can multiply by anything else and get back that other thing. So what would the -1 be in this group, or in this ring? What would the additive inverse of our multiplicative identity be then, in other words? Where our multiplicative identity is 1, 0, 0, 1. Hey, tease Professor Pytel about this later, right?
-1, 0, 0.
Yeah. It's just going to be the negative of that matrix. So if we were to take -1 times any element A, we're always just going to get back the additive inverse of A. The additive inverse of the multiplicative identity times any element A is always the additive inverse of A. That's a fancy way to say -1 times A is -A, but that's what that equation really means. Secondly, if you were to take -1 times -1, you're going to get back +1. So in other words, if you were to take the additive inverse of the multiplicative identity and multiply by the additive inverse of the multiplicative identity, you're going to get back the multiplicative identity. Bit of a mouthful. But it ultimately just means -1 times -1 equals 1 in whatever ring you're looking at. And finally, I don't know why I have these in a separate section 1 and 2. I'm just going to say if R has multiplicative identity 1, then it's unique. So in other words, if we have a multiplicative identity element in the first place, then it has to be unique. There can't be multiple multiplicative identities. And second, multiplicative inverses are unique if they exist. If A has a multiplicative inverse, and typically the multiplicative inverse of an element A, you're just going to write as 1 over A, then it's unique. So these are properties, these are like kind of the first properties we proved back in looking at groups, that the identity element's unique, inverses are unique. Here, I'm saying the same thing has to hold true for multiplication if you have an identity element in the first place and if you have inverses in the first place. If these things exist, then there can't be more than one of them. Any questions or comments? Yeah, Dave?
Why are they called rings?
Why are they called rings? Don't you know? Because the integers form a ring. If you go forward enough, then the integers like get really big, more and more positive integers. Eventually, you'll wrap back around.
What?
Is positive infinity equals negative infinity. You may think I'm just being silly, but that's actually a big part of kind of, there's some geometric ways that we're going to look at rings. We haven't talked about them yet, but we will in a couple weeks from now. And then the definition for ring that will make a bit more sense. But it kind of refers to the cyclic nature of the integers is kind of the short answer to that question. All right, I'm going to prove that if we multiply by 0, we're going to get 0. Is that something you'd ever thought you'd do in a math class, prove that if you multiply by 0, you get 0? See what happens when we do that. What's that?
I'd rather do that than prove NP equals N.
Oh, God. NT equals N? Wait, what? NP equals P?
Yeah.
Is that what you're saying?
Yeah.
Oh, well, that's, I'd much rather prove NP equals P, because if I prove that, I become like a millionaire. Whereas proving A times 0 equals 0 gets you a pat on the back. All right, let's prove this. So I'm on the next page of the packet now if you're following along. We're going to prove A times 0 equals 0 times A for all A in our ring R. So here's my proof. I'm going to let A be an element in my ring. Then if I were to take A times 0, by definition, I claim that's going to be equal to A times 0 plus 0. Why is that? Because 0 is the additive identity. So if we added the additive identity to itself, we're just going to get back itself. That's like saying that would be like saying in an arbitrary group that if we were to take the identity and then combine it with another identity, we're just going to get back the identity. So 0 equals 0 plus 0. But what does the distributive property tell us is another way to write A times 0 plus 0? Here?
Parentheses A times 0 plus more parentheses A times 0.
Yep, A times 0 plus A times 0. So A times 0 is equal to A times 0 plus A times 0. Now we can just subtract A times 0 from both sides. And on the left side, if we start with A times 0 and we subtract away A times 0, what are we going to get? were to subtract A times 0 from A times 0? Yeah, the additive identity by definition. Any element minus itself, meaning plus its own additive inverse, has to give the additive identity, which is 0. And on the right, if we have A times 0 plus A times 0, if we subtracted away a single one of those, we're just going to get A times 0. So A times 0 equals 0 in any ring. And I don't feel like proving 0 times A equals 0 because it's basically the same proof. So here's a quick corollary. It's the same proof, just reverse things and use the other distributive property. So here's an interesting corollary to this. Unless 0 equals 1, Dr. Gerstle, what the bleep do you mean by if 0 equals 1? Unless the additive identity and the multiplicative identity are the same element, R does not form a group under multiplication. And as our quick and really quick proof for that, why doesn't R form a group? It's basically because 0 can't have a multiplicative inverse, because 0 times x equals 1 has no solution. Unless 0 equals 1, 0 times x equals 1 has no solution. Why? Because 0 times x, no matter what your x is, should always give you 0. So 0 has no multiplicative inverse. And how many rings do you think there are where 0 is equal to 1? Where the additive and multiplicative identities are the same? Turns out there's exactly one ring where that happens. And the only ring where that happens is the ring with only a single element in it, the trivial ring. Turns out the only way you can have the additive and multiplicative identities be the same is if your ring literally has nothing in it but that single element. So there's the answer to your question. Do we have a special name for when a ring does form a group under multiplication? We do. It's the trivial ring, the ring with just a single element in it. So that's all we have time for today. When we come back on Monday, we're going to talk some more about properties of rings and start getting into the discussion of what is a subring. And talk about some subring tests. Kind of doing the same stuff we did in group theory, but kind of a lot faster because we've already done it once. We're just adding a new operation now. So hope you all have a good week. Don't forget, homework 6 due tonight. Hope you all have a good weekend. See y'all on Monday.